All right, and welcome back, everyone. So, like I promised in the last, hopefully, the last part of this video series, we're gonna go over the solution. We're gonna actually solve this differential equation. So, all right, I have my boundary conditions at zeta. By the way, that's the real name, zeta. We're just gonna go along with squiggle. At squiggle equals 0, theta is gonna be equal to 1, and at squiggle equals 1, the derivative of theta is equal to 0. All right, and just to point out, I made a mistake in part 2. I wrote theta equal to 0 where it's supposed to be 1. Okay, all right, we're making the boundary conditions dimensionless along with our differential equation. Okay, so we're going to use the general solution. All right, and any good differential equations textbook will have an appendix where you have all the nice solutions. And this is a linear differential equation. This is a linear homogeneous differential equation. And those have been solved by people who are way smarter than I am. And you can use their knowledge at the back of their textbooks in the appendices. All right. So the appendix that I'm using is Bird Stewart Lightfoot Introductory Transport Phenomena, first edition, Appendix C, I believe. Appendix C from BSL, Bird Stewart Lightfoot. All right, the OG Transport Phenomena textbook. So this is the general solution, right? Theta as a function of eta, a zeta, a squiggle. All right, we gotta be consistent with our terminology. Squiggle. All right, C1 and C2 are my constants. C1 and C2 are the constants that I have to solve for using my two boundary conditions, two unknowns, two equations. Very good. So the first boundary condition number 1 is going to be not so bad, right? So let's put that right here. Theta is equal to 1. And what's the let's see what this becomes. Actually, let's walk through this. C1, I'm going to switch color schemes around. Cosh, hyperbolic cosine, square root of the BO number times 0, plus C2, again, nice colors, sinh, sine, hyperbolic sine, whatever notation, whatever terminology you use. Now, okay, so basically what you're taking is you're taking the cosh of 0 and you're taking the sinh of 0. And if my memory, if my high school mathematics memory is good, then this entire term comes out to be 1, and this entire term goes to meet its maker. All right, bye bye. So with that said, 1 is equal to cosh 1, sorry, is equal to C1. Oh, yeah, C1. That's hey, yo, give yourself a bat. That's a good one. Yay. So what about the next one? What about C2? So for that, we'll have to use the second boundary condition, and for second boundary condition, we have a derivative term. So yes, we'll have to take the derivative. And just to point out, this is the derivative taken at eta equals 1. Okay, so if I want to be accurate with my notation, good. So this right here, I took the derivative. I did some recon, and this is what turns out to be the derivative. Okay, and if you guys feel like I've made any mistake, please let me know in the comments. So yeah, this is equal to 0. The derivative is equal to 0 at eta equals 1. So let's see. And by the way, C1, we're gonna use this C1. We already know C1, right? So forget about that. BO sinh of square root BO times 1. Not sine, my bad, sorry. Sinh, the hyperbolic sine, not to be confused with the trig sine, okay? Hyperbolic sines and cosines. Square root BO times cosh of square root BO, okay? And add all that mass equal to C2. Okay, all right. So again, sorry about this. This was me working ahead. So let's see. This was my second equation. This turns out to be 0, and this turns out to be 1. With that said, 0 is equal to nothing. Boom, boom, bye. C2. So we have square root BO number. Square root of BO number. Actually, no, my bad. This is not 0. This is not 0, and this is not 1. My bad. Sorry. Yeah, I thought I could play around with the algebra. I was a fool. Sorry. C1 is 1. Okay. C2, however, I can solve for C2. I can solve for C2. C2 turns out to be, hopefully I won't mess up this algebra. The negative of square root BO times sinh of square root BO divided by square root BO times cosh of square root BO. All right. Bye-bye. And C2 comes out to be negative tan hyperbolic of square root BI. C2. All right, how's everybody doing? So hopefully I won't forget this negative sign. And C1 was just 1. All right, and our original expression, let's just grab our original expression while we can. Let's just use technology. All right. I got it. Okay. All right. Here we go. All right. So from our general solution, we're going to go to the solution for our problem. I forgot the correct terminology, the correct differential equations terminology. If you guys remember, please let me know. Theta of zeta. And zeta, by the way, is squiggle. C1 is 1. So this becomes cosh square root BO times the squiggle. Squiggle is our independent variable. C2 is negative tan hyperbolic. So this becomes negative sinh times tan never mind. Tan hyperbolic of square root BO negative times sinh of square root BO and squiggle. So this right here is the solution. This right here is my dimensionless temperature profile. And if you refer to the textbook, the section in chapter 10, I believe, that talks about cooling fins in BSL, they use an identity. They use, I believe, an identity to go from something like this to, let me just check. Hold on, give me 1 minute. Okay. Yeah, something that looks like this. Something that looks like, give me 1 second. Yeah, something that looks like this. Cosh of, yeah, they're using some identity. That I am not really aware of. My mathematics is hitting its ceiling. 1 minus eta. So this is the format in which it's been given in the textbook, if you're following Bird, Stewart, and Lightfoot. And how do they get from this to this? That even eludes my understanding. They're probably using some algebraic identity that I'm not aware of. And if you guys can find that out, please let me know. I'll give you guys a thumbs up. So yep, this right here, if you want to follow Bird, Stewart, and Lightfoot, then that's what they're doing. This is the solution found in BSL, Bird, Stewart, Lightfoot. And yep, so I think that pretty much wraps it up. Gosh, no mistakes, no mistakes. All right. So yeah, guys, thank you for sticking around, by the way. We started off, let's just see what we've done. Wow. 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 Okay. Ooh. Okay, even my tablet is kind of picking steam. So yeah, cooling fin, application of conduction, extended surface. Why do we worry about these? They increase surface area, and increasing surface area enhances heat transfer. More heat, if you have more surface area, you'll have more area to exchange heat. That's going to enhance the rate of heat transfer. Okay. So the reality is often disappointing, which is why we're going to use assumptions to make our model simpler so we can get an analytical solution. Again, this can be done in something like COMSOL or ANSYS, and that's usually a good project. Okay, if you want to really boost your resume. So if you want to get a more accurate model, you can use something like COMSOL or ANSYS, and they solve partial differential equations numerically. Shell balance. Okay, this was our shell. Okay, our temperature is varying along z, so that's the shell. That's the shape of our shell. All right. Um, heat conduction coming in, conduction going out, and convection going out. In minus out is equal to 0 at steady state. Blah 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 blah. Math. Oh, I got my final ODE, which was non-homogeneous and would have been hard to solve. So I introduced dimensionless variables. Not to forget my boundary conditions at z equals 0, the wall temperature. At z equals 0, we have the wall itself. So we had temperature of the wall. And at z equals L, we had an adiabatic tip. So no heat flux. So from non-homogeneous to homogeneous, we introduced dimensionless variables, dimensionless length, dimensionless temperature. Woo woo woo, magic, algebra, calc, calc. All right. That's a nice looking differential equation you got there. Mind if I use a general solution? Okay, that's exactly what I did. And I got my constants of integration, C1, C2, and again, this is the result I got, this one. And this is the result that my boys Bird, Stewart, and Lightfoot got. So follow whichever one you like. All right. And thank you so much for sticking around. All right. Good luck.